Hi, hello, how are you? Welcome to this CodeRage 2018 session on machine learning for engineers. My name is Craig Chapman. I'm a software consultant for Embarcadero Technologies, and on the screen now you can see my Twitter handle, my email address, and the address of my blog. First up today, I'm going to explain why I added for engineers to the title of this session. This is an introductory session to introduce machine learning to software engineers. I'm then going to talk about the notional comparison between artificial neural networks and real neural networks, followed by a walkthrough of how to process the computation for a neural network. We'll then take a look at how to train the neural network by feeding an error signal back through that network. I'm then going to introduce you to dark vectors, which is my own vector math library, which we'll be using in today's example. And then I will run through the example source code of building and training a neural network. And of course we'll have a little time left over at the end for some questions. So why did I add for engineers to the title of this session? Well, in discussing machine learning today, I'm going to introduce you to neural networks. And that is going to involve talking about the comparison between real biological neural networks and artificial neural networks. Now, I am not a biologist by any measure, in any sense of the word, and so my description of the biological process which inspired artificial neural networks is going to be crude. Similarly, I'm not actually a mathematician of any kind or a statistician, so when I discuss the mathematics behind neural networks, I'm not going to be going into too much detail on this. I'm not qualified to do so. My aim here is not to give you a deep understanding of the calculus or statistics theories behind neural networks, but instead to give you a practical working example of a neural network with a training algorithm and some source code that you can study. So we're aiming for a software engineer's practical introduction. The one thing you will need in order to follow along today is an understanding of some basic vector matrix math operations, and nothing too much beyond that. If you don't understand vectors and matrices and dot products and so on, then it's worth doing a little revision, but it is not difficult mathematics. This is high school level mathematics, so I think you should be able to follow along. Okay, so let's talk about the real neural network inspiration for artificial neural networks. What we're looking at here is a typical biology textbook illustration of a neuron cell. There's an estimated 100 billion of these in the human brain. So in the crudest sense, this is the biological equivalent of a transistor in a computer. It's the smallest data processing unit of the brain. The dendrites, which are labeled at the bottom, are the inputs to that cell, and the electrical signals which are generated by the cell travel out through the axon, so that would be its output. So these electrical signals stimulate the dendrites, they cause stimulation in the cell, and when there is sufficient input on the dendrites to overcome some threshold, then the cell is said to fire, and that is, it transmits its signal along its axon. Signals traveling through the axon reach the synaptic terminals and are then emitted through the synapses. So the synapses are the gaps between the synaptic terminals of this cell and the dendrites of other neuron cells. So in this way, neurons are wired together to transmit a signal, which is manipulated and modified as it passes through each neuron cell. And as it passes along a pathway of neurons through the neural network, that pathway is strengthened. So that increases the likelihood that the pathway will be taken again for a similar input. So in this way, real neural networks are able to learn by strengthening the connections between the neurons. In the interest of brevity, I'm going to skip over the attribution of several neurophysiologists, mathematicians, and computer scientists here, but suffice to say that this understanding of real neurons is sufficient to give us the artificial neural networking technology that's in use in machine learning today. So this is my attempt to diagram an artificial neuron. It's akin to the diagrams you'll find in most textbooks on the subject. The cell body in this case, depicted in blue, takes as some input data presented on its edges. The edges depicted in yellow they resemble the dendrites of a real cell. And so these carry the data signal into the neuron. Within the neuron, a function called the activation function modifies the data from those edges and presents the result as its output. This is approximately where the similarity between real and artificial neural networks ends. Before we look at how we simulate a neural network, let's consider the differences between the hardware of a real and an artificial neural network. So real neurons in mammalian brains fire around 7 times per second in operation, and this is in accordance with the alpha wave frequencies of the brain. So 7 firings per second is not very fast at all if you compare this to, say, the basic unit of processing in a computer, the transistor. The transistor is going to switch several million times per second. So how is it that real brains can perform such a wide variety of computational tasks at high speeds? Well, the answer is parallelism. I think I mentioned earlier that there are around 100 billion neurons in a human brain, and these are wired in parallel, all operating at the same time. Now, because transistors in a computer are wired in strict series arrangements for sequential operations, the closest actual representation of a compute unit is actually a CPU core. And since CPUs today typically don't have more than a handful of cores, they don't compare in terms of parallelism to a real brain. Now, it's worth keeping this in mind as we look at how we model an artificial neural network. It's a key to understanding why we model them the way we do. Parallelism is behind how we structure the model. Another key difference to the way that we model neurons is that it's not typical to simulate neurons firing, but instead we simulate them as having input values and an output value. The inputs to a neuron are generally the outputs from some other neuron. So I've written in some example values here. On the inputs we have 0.25, 0.30, and 0.35, and each of the previous neurons is connected to this neuron by an edge. Now, the edge has a weight associated with it. So the weights that I've written here are 0.125, 0.175, and 0.225. So the artificial neuron multiplies the input value, which is the output of some other neuron, by the respective weight, and then sums the result. And in this case, we get a result of 0.1625. We then pass that result through a function called the activation function. In this case, we're using the sigmoid activation function, and this serves a couple of different and quite distinct purposes. So the first purpose is to decrease the range of possible output values for the neuron to a predetermined space. In this case, the sigmoid function is reducing our neuron output to values in the range of 0 through 1. This means that even if the sum of our input neurons to this neuron exceeds 1, then our neuron will only ever output values between 0 and 1. It will squash that result into that space. This helps to prevent floating point values from scaling outside the range of precision that's available in most processors, and helps us to have a larger precision on the floating point, so more decimal places. The other purpose of the activation function is to attempt to fit the data that we're getting from our inputs into some kind of a curve. Now, as the sigmoid curve is fixed, the only way we can map our data to the curve is to adjust the inputs, which we do by adjusting the edge weights. So we adjust these weights to distort the data that's coming in towards a fit with that sigmoid curve. So the output is as close as we can get to that curve for the given input. Now, most of the problems that we can simulate with a neural network can't be fit into a simple curve. However, multiple neurons, each with their own edges and weights and their own sigmoid curve to map to, can be modeled into more complex curves. So we can create larger curves and shapes that we can model our data to. And that gives us the ability to address more complex problems. So it's worth noting here that there are many possible options for your choice of activation function. The sigmoid function is commonly used in educational material when teaching machine learning because of its flexibility. But while it is a very good general purpose function, the sigmoid activation function is not the best function for learning in most cases. In fact, it's far more common to use a function called ReLU or ELU, and this is because ReLU and ELU are quicker to train, but they are also for more specific purpose networks. So this is all getting a little out of scope for this session. We're going to be sticking with the sigmoid function. I just wanted to make you aware that there are other options for your function here. Now, before we complete our look at the neuron and how to simulate a neural network, I want to take a brief moment to explain one more feature which we'll be using, but won't be looking too closely at today, and that feature is the bias value for our neuron. So a bias is an additional input to the neuron, which we set a value for each neuron or for each layer of neurons. So suppose our weights are adjusted as best they can to make our problem fit the sigmoid curve, but our curve is out of phase. In the diagram you can see that the blue line indicates our sigmoid curve and the red line is our out of phase result coming from the network. So what we need to do, if you look at that red line, it's shifted by about 0.5 in the x-axis from the true curve. And this is where the bias comes in. We can add the bias value to the sum of the neuron's weighted inputs before passing it into the sigmoid function. And this bias can be used to then pull that curve back into alignment with our sigmoid. So in our example, we might use a negative 0.5 bias, and that would bring our red curve back into alignment with the activation function. Now we refer to the bias value and the weights for our edges as free parameters. These are the parameters that have to be adjusted and tuned in order for our neural network to learn. In inverted quotes there, learn. So in our example today, we're going to look at how to adjust the weights of a neural network, but we're not going to adjust the bias. It's just not necessary in such a simple example as we're going to be covering, but I will include the bias in the source code so that you can see how it can be used and where you might adjust it in your own experiments. So let's do a quick walkthrough of how a neural network functions. So what we have here is a diagram of an artificial neural network, a pretty typical introductory neural network. Now in a real brain, neurons are arranged very organically. They're all in continuous service and in parallel. In our computer simulations, we don't have the luxury of that kind of parallelism, and so we have to arrange our neurons differently. Typically, the artificial neural networks are arranged into layers, and this diagram is a typical example. So on the left, we have 3 input neurons, I0 through I2, and in the middle we have a second layer, a hidden layer of neurons, H0 through H3, and on the right we have 3 output neurons, O0 through O2, so output 0 through output 2. Now in the simulation that we'll build later today, we're actually going to be using this precise configuration of neural network. I'm basically going to be training a neural network to count in binary. So if we present 0, 0, 0 on the inputs, we want to get 0, 0, 1 from the outputs. If I present 0, 0, 1, I want 0, 1, 0 on the out. So I'm basically going to be using this with 3 input neurons and 3 output neurons and 4 hidden layer neurons. Now calculating the number of hidden layer neurons is more of an art than a science, but there is a general rule of thumb. And that rule of thumb is that you sum the neurons in the input and output layers and divide by 2. So you get the average number of neurons across the 2 layers. Now it just so happens that through experimentation, I've found that it's quicker to train a neural network to count in binary if you have 4 neurons in the input layer. So the rule of thumb, it will train, it will work, but it's a little more efficient to add the additional neuron. So in our simulation, we would place the input data onto the input neurons here and process the sums of them with the weights connected to the hidden layer. So you'll see here that we have every single one of our input neurons connected by an edge to a hidden layer neuron, and in fact to all of the hidden layer neurons. They're all interconnected, and each of those edges has a weight associated with it. So we're going to multiply the values coming from the input neurons by the weights and present that as a sum into the hidden layer neurons. So the hidden layer neurons then activate the activation function. They're going to translate that input into the sigmoid function, and then we're going to repeat this whole process again, taking the hidden layer values, pushing them through the edges, which are weighted, into the output neurons. And we do this again by summing the multiplied weights by previous layer values. So each neuron in our input layer is connected by a weighted edge to each neuron in the hidden layer, and then again each hidden layer is connected by a weighted edge to our output layer. So we're therefore referring to these layers as being fully connected. There are other approaches to modeling neurons, but this approach is by far the most common, and it's the most common for good reason. If you consider our input layer as a column of 3 values, what you have is a simple vector. Similarly, the weights can be represented as a matrix. So this matrix has 4 rows, one for each of the hidden layer neurons, and it has 3 columns, one for each of the input layer neurons. So we can repeat this process to represent the hidden layer neurons as a vector, and the weights connecting the hidden layer neurons to the output as another matrix. So finally, we'll add one more vector to represent the output neurons. And from an engineering standpoint, I just love it when more complex problems can be represented as simple vectors and matrices. This arrangement allows us to perform a large number of operations on this data using algorithms that are optimized for parallel processing. So today we'll be simulating our small neural network example on a single CPU core in single-threaded code. However, it's not uncommon for larger neural networks to be processed using graphics hardware, which is specialized to handle lots of floating point operations in parallel. So we'll talk about that a little more later. For now, however, I hope it's clear why we arrange our neural networks into layers, and while each layer can be processed in sequence, why the vector and matrix operations performed in each layer can take advantage of parallel processing across multiple cores. In fact, in more advanced scenarios, there are even more advantages to this approach, which again we can discuss later in the session. So let's take a walk forwards one step through this network to see what happens when we simulate it. First, we place our input data on the input neurons. So we're literally putting in our values of 0, 1, 0. If I'm doing a counting in binary, I'm entering in the value 0, 1, 0. We're just literally going to set those values, those neurons, to 0, 1, and 0 respectively. Then we're going to take the dot product of the first weights matrix with our input vector. And what we get will be the values for the hidden layer. So now that we have the hidden layer values set in this vector, we take the dot product of the second weights matrix with those values, and we get the output layer. So this is really simple. It's just a couple of dot product operations to process the input through to the output. And this is really advantageous because moving the data forward through the network is querying the network. It's saying, here's some input, give me your prediction of what the output should be. And once a neural network is trained to perform a task, the training can be as compute intensive as it needs to be, but we want the task to run as quickly as possible. We want the machine to be able to perform as efficiently as possible. And this is quite an efficient system. So far, I've omitted the bias in our calculation. It's actually trivial to add it in, but I'll demonstrate how we do that when we get to writing some code. For the moment, however, this is all we need to do in order to query our network. We just do the dot product of each layer of neurons with the matrix that connects it to the next layer. So now assume for a moment that you have assigned entirely random values to the weights in your matrix. You apply some input, run through the network to calculate the dot products of each layer, and what do you get as a result? The answer is random junk. This neural network is useless because random values assigned to the weights are just going to generate random outputs. What we need is some way to adjust those weights so that we get the desired output or the target output from our computation. And that's where training a neural network comes in. So we're going to take a look at the most commonly used training algorithm known as backpropagation, and it's the backpropagation of an error signal. So we're going to take an error signal from the output based on the desired output and the actual output of our network. We're going to calculate an error, and then we're going to send that error signal back through the network. So we're going to backpropagate through the network the error at various stages. So let's go ahead and take a look at how we do that. So training this typical network depends on the type of function that we expect the network to perform. To the best of my knowledge, there are three primary categories of function that we can perform with a neural network like this one. The first is a regression problem in which we have some data set for which we have known outputs, and we want our neural network to learn how to convert inputs to outputs. Now, we don't want it memorizing. So for example, if you had a data set containing the square footage of the floor plan of a number of houses in your own neighborhood, and you then have the prices that those houses sold for, you could reasonably expect that there's some relationship between the square footage of the house and the sales price. So you can train a neural network on the data that you have, and you hope to create an algorithm which is able to take the square footage of any property as input and predict the sales price as an output. Now, the goal of this problem is to predict the sales prices of houses that appear on the market regardless of the network having seen the precise square footage in advance. If it could only predict examples for which it's seen data already, then it wouldn't be any better than a lookup table. So what we want is for the network to learn how to generalize the translation from the square footage to the price of the house. And you could also add additional factors, like you might want to add in local amenities, local trends, all that kind of stuff as inputs to your network. But this is effectively a supervised learning problem. So we're telling our neural network, here's the input, this is what I expect as output. That's supervision. So the second type of problem that we could apply to this type of network is one of classification. So for example, suppose we have the neural network given a set of pixel data from a handwritten character that had been scanned in. So we want the neural network to classify that image as we present it to the machine. We want it to be classified as a character from the alphabet. So this too is a supervised learning problem in which we provide the network with a whole bunch of existing data. So a bunch of handwritten A's, a bunch of handwritten B's and C's and so on. And we tell it for each one what the expected output is. We tell it we expect you to find this is an A, this is a B, and so on. Once we've trained the network, we can then present it the handwriting from someone that it's never seen before, and the goal is for the network to be able to identify the characters in that unknown handwriting. It doesn't need to have seen those characters to recognize them. So we're not going to be looking at a classification example today, but effectively the technique that we're using to train our network is exactly the same technique for both of those two scenarios. There is a third and final type of problem that we might be able to present to a neural network like this, and it's one that is not supervised. So suppose we're writing a neural network that we want to have it compose some new piece of music. We might want to feed it a number of pieces of music from various composers and have it identify for itself the features of that music that make it melodic and enjoyable, and then to generate its own piece of unique music as output. Now, it would be, as a primary goal, it would be to generate a piece of music in the same style as the composers that it was trained on. So this type of neural network is, or this type of problem, it's the same type of neural network, but this type of problem is one that we're not going to be looking at today and would require some modification to the algorithm that we're going to learn today in order to work, but it is based on the same techniques. So while it's a very different type of problem and a different training algorithm, the techniques that we learned from this session today can be applied. And if you want to know more about this type of neural network problem, I strongly suggest you read up on something called a restricted Boltzmann machine. So we're going to look at a method for adjusting our neural network based on a supervised learning situation. This means we have data for the input and there's a known correct output that we want the network to generate. So we first need to determine how far our network output is from the desired target output, and then we need to adjust the weights of the network towards the correct output. So let's first look at a way of calculating how wrong our network is. So we run a query with some inputs and we get an output on the network. And what we want is simply the delta rule. This is simple enough. This is just the target less the output. So you subtract the output that you get from the query from the target that you expected or that you wanted from the network, and that gives you the delta, the difference between the two. Now, what we actually want for our training algorithm is the negative of that. So I'm subtracting the result of target less output from 0. This is just the way that it's written in most textbooks. You could, of course, do output less target, so that would give you the same result. Okay, so we have our delta. We know what the difference is between what we got and what we wanted. In fact, this is all we really need to start training the network back. Now at this point we could put together an algorithm which computes all of the accurate values for our weights and causes our network to produce the correct output first time. However, if we did that, it wouldn't actually be very useful to us. See, the problem is if we adjust for this one specific training example, then any future data that were presented to this network, it would not identify correctly because it would expect that input to be the same as this example. And as soon as we train on a second example of data, it will forget everything it learnt about the first example. So we don't want an algorithm that is going to perfectly adjust the network for this one training set. In fact, what we really want is just to adjust the weights of the network in a small step towards the correct output. So in this way, we're going to nudge each of the weights on the edges in our network in the right direction, and we're going to repeat this step for multiple data points, and we'll repeat our set of data points multiple times. We're going to repeat this in iterative loops until the network is producing a consistently reasonable output. So how do we do this? Well, Our error delta already provides us with the direction that we need to adjust the weights towards the correct output, because the delta can be both positive and negative, so it has direction within it. What we need to determine is how big a change is needed to adjust the output from a neuron just one step in the right direction. And so what we need to do is calculate the derivative of our activation function for the output values. Now, I'm not going to go into too much detail about how to calculate the derivative. It's quite well documented online how to derive the sigmoid function. However, I would like to explain just a little about what calculating the derivative is doing. So if we take another look at our activation function, this sigmoid function here, you'll notice that parts of the curve are steeper than others. So suppose our network has generated a 2 as the value for its output on one of the neurons, but the value we wanted to come out of there was a 0. Well, looking at the x-axis, our delta tells us that the difference between these 2 points is -2, right? So we go from 2, -2, we're back at 0. So we already know which direction to adjust in, but we can't simply subtract 2, that would overtrain the neuron for the problem. And also, a small step backwards from the position of 2 on the x-axis would yield a far smaller change to the network's output than if we did the same size step backwards from position 1 on the x-axis. And the reason for this is that the slope of the function is more steep at position 1 than it is at position 2. So what we need is some way to normalize the measure of the slope at the point for which our neuron generated its output of 2. So we need to take the derivative, and pretty much any vector library will enable you to take the derivative of your neuron values. So I'm not going to look too closely at how we do this right here, just know that your math library should take care of that for you. And so the derivative now gives us a step size for one position movement, or the smallest possible movement along our curve. Now if we take our derivative and multiply it by the delta error value, what we end up with is the delta error, so that contains our direction, scaled to the slope of the activation function. So that is, we get the delta for one small step in the direction of our target. So as it turns out, this is still actually a little bit larger a step than is useful for training our network, but we'll scale it a little bit further later. What we need to do next is to determine how much of this step needs to be assigned to each of the weights on the edges attached to our output layer. So in order to nudge those weights in the right direction, we need to divide up this gradient value. Well, each weight relates to an edge which connects the neuron in this layer to a neuron in the previous layer. So let's suppose one weighted edge is connected to an output neuron and it's correctly contributing to the correct answer. But another edge connected to the same output neuron is contributing heavily to the error on that neuron. So if we simply adjust the weights for the output neuron by the same amount, we'll basically be making a corrective movement in the edge which was causing the error, but we'll also be damaging the edge which was behaving as it should. So essentially we would just swing the error from one edge to another. We need a way to proportionally distribute our step across those edges. And the way that we do that is to use the hidden values as our guide. So H0, if H0 outputs a large value, then we consider it a large contributor to the edge multiplied values in O0, O1, O2. If H0 outputs a small value, we consider it a small contributor. So we can use those neurons as our guide for how much to apply to each of the weights in that matrix. And so what you can see on the screen here actually is the adjustment matrix. So the adjustment matrix is a matrix containing the values for the amounts that we need to adjust the weights in this layer. So what we're going to do is take H0, which is our hidden 0 neuron, and multiply it by the first element in our gradient vector. Remember that delta and derivative and gradient are all vectors. So effectively, if you look at how the matrix is arranged, you'll see that the H0 through H3 neuron vector is being laid across the rows of this vector, and the gradient is being multiplied in by the column. So it's going down the columns. And that multiplication is on a per element basis, so this is a Hadamard multiplication as opposed to a dot product. So this gives us a matrix which contains the amounts which we must adjust our weights by, and that adjustment is a simple subtraction. We just subtract each of those calculated values in this adjustment matrix from the weight matrix that provides those connections. But we're not going to do that subtraction just yet. First of all, I said that the gradient is still a bit large. We're going to introduce this learning rate. So this is a constant. It can actually be a variable in some training algorithms, but for our purposes today, this is a constant. So let's suppose that the learning rate was 0.5. Well, by multiplying the adjustment matrix by 0.5, again, a Hadamard multiplication, what we're effectively doing is halving the adjustments. So we're adjusting how quickly the adjustment should be made to the layers of the network, and therefore adjusting the rate at which the network learns. So we do need to do that, and we still don't want to subtract these adjustments yet. This is the complete calculation for this layer, but before we subtract the adjustments from our weights matrix, we need to use that weights matrix in the calculation for the next layer back. So let's see how we do that first. Okay, so we have our adjustment values for the output layer. How do we calculate the adjustments for the hidden layer? Well, it's more or less the same calculation, but we need to adjust our gradient. So the contribution of the hidden neurons to the error has already been accounted for in the output layer, and so we need to account for that contribution as it relates to the input layer. So we're looking at how much the input layers contribute to the malfunctioning, if you like, of the hidden layers, the error in the hidden layers. And we also need to adjust our derivative, because the derivative we took in the previous layer calculation was of the output layer. Now we've moved back to the hidden layer. We need to use the hidden layer neurons for our derivative calculation. So the first thing we'll need to do is to transpose the weight matrix for the hidden and output layer. So the layer we've already calculated adjustments for, the hidden output layer, we need to transpose that matrix. Let's see why we need to transpose it. So this I'm going to just refer to for the moment as the HO matrix. This is the hidden output matrix. And it's not the one we're trying to adjust, it's the one that we've already calculated adjustments for, but we need to take it into account when we calculate our gradient coming back. So we need to take this into account as we calculate the proportion of the error signal which propagates back into our input hidden layer. Okay, so the way that we do this is we take the dot product of that HO matrix, but we need to take the dot product of the transposed matrix, and that will give us our new gradient, effectively, our new signal strength. Now, the reason that we use a transposed matrix is this. If you take a look at the number of neurons in the hidden layer, we've got 4 in there, and we're trying to send back a gradient signal that we calculated in the previous step, which only has 3 elements in the vector. And you can't do a dot product on a matrix and a vector if the number of rows in the matrix is not matching the number of elements in the vector. So what we do is we simply transpose the HO matrix. We're working backwards here, so we can use the matrix transposed, and transposing it effectively flips the width and height of the matrix. It flips its dimensions. So that allows us to do our dot product computation on it. And so we can then calculate our gradient as the signal, which is the gradient from the previous layer, dot producted through the transposed HO matrix, multiplied by the derivative, this time the derivative being of the hidden neurons. Okay, and then the calculation is basically the same. In the matrix we have, again, across the rows of the matrix we have the input neurons this time, so the inputs to this layer, and down the column we have the gradient vector, which is now a 4-element vector. Okay, so that's pretty much it. That's all we need to do to train our network. We can now take those 2 adjustment matrices that we've calculated and subtract each of them from their respective weights matrix. And that's going to nudge our neural network's processing in the direction of the correct output. And we're going to have to repeat this many, many times for a variety of different inputs for the network to generalize on an algorithm to generate the output. So before we go through this in code, one thing we're going to need is a vector math library. Now there are lots out there, and many of them are more complete than my own dark vectors library, but dark vectors is the one that I'm going to be using in the example here today. So I'm going to take a moment just to introduce you to the library. So dark vectors is available at the URL that you can see on the screen, and that URL will also be on the blog page which accompanies this session. Dark Vectors is a math library that I've developed as part of two larger projects. So one of them is actually a deep learning machine learning framework called DE Compute, which is very close to being a release-worthy system now. And the other part is a video game engine that I'm building. Now, this library, Dark Vectors, is still quite incomplete. It's missing more or less everything it needs for game development, but it is already quite usable for AI experimentation, which is why I'm using it for our sample here today. Dark Vectors provides a Pascal-like syntax to working with vectors and matrices through operator overloading and advanced record types. So you can declare a variable of type vector, and you don't need to worry too much about the elements of that vector. You can just add vectors together as though you were adding scalar values with an addition operator. So that makes it convenient to work with vectors and matrices. So the default Dark Vectors implementation provides a single-threaded implementation, single core. However, the library has a plugin-based implementation system, so it allows for more advanced parallel processing implementations to be plugged in. And there is actually currently a GPU acceleration plugin for Dark Vectors. So Dark Vectors itself is open source. It's available under the MIT license. The GPU accelerated implementation is closed source but freely available to use. It's currently pending release. And I have a network distributed computation implementation planned for about the middle of next year as well. So if you're interested in seeing this library progress, go check it out at digitalenvysoftware/open source. Okay, so let's go ahead and dive into the example. Now, I've pre-recorded myself writing this code, and I'm effectively going to narrate over the top of myself coding. Basically, I've implemented this type of neural network so many times now that I can almost do it from memory. And so effectively, I just wanted to write the code, make sure it worked, and I will narrate over to explain what we're doing and how that relates back to what we've looked at so far. So what I've done in this example is I've trained the neural network to count in binary, as I was describing before. It's a 3x4x3 network, and I'm going to present inputs 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And I wanted to give me the input plus 1 in binary. So let's go ahead and get started. Okay, so the source code that you'll get when you download the code for this session will include the Dark Vectors library at the current revision, and of course the project that we're going to create right now. So we'll go ahead and create a new console application. There's no graphical output to this application, and then I'm going to go ahead and save that off as binary counter. Now, in order to make use of the vectors library, we're going to need to build it first. So I'm going to go ahead and open up the project group for the Dark Vectors application, and I'll use that group to add our binary counter application to it. Okay, and for convenience, I'm going to go ahead and save this group off as a binary counter group in the root directory of our source. So you can just open this one group and build everything from here. Now I need to do a build of all of these libraries, but first I need to add the Win64 target platform to my project, because all of the other libraries default to Win64. You can build them with just about any target. So we'll add Dark Vectors to our users list and put a input vector into the source code, and we'll know that our code is compiled when it can recognize this new type. And one of the things you'll notice as I assign the input here is we can just assign a literal array as a vector, which makes the syntax for working with vectors quite convenient. Now I'm going to come up to all platforms and set my search path to include the output directory for Dark Vectors. So that's out lib and then the target platform. And with that done, everything should build. Okay, some warnings, but our code builds. We have access to the Dark Vectors types. So the next thing I'm going to do here is create a function for running a query against our network and have it display the results of a query that we run. So I'm just going to put in a title for whatever this query is. So we'll give, untrained experiment, trained experiment, and so on. And then an input vector, which will provide the input that we're going to query the network against. We'll need a variable to receive the output from our network. And then we're just going to write line to the console to display the output. Okay, so I'm going to add a new unit here, which is going to contain a class, which will be our neural network. And that class is going to be T neural network. Now initially I put override on the constructor here and then realized later that I actually need that to be reintroduced. But for right now I'm just going to override the constructor and the destructor. We'll start by adding a method to query the network. So we're going to pass in an input vector and we'll receive an output vector as a result. Of course we need to use the dark vectors library in this unit. And then here in the main program I'm going to create a neural net variable to contain an instance of our class, and we'll go ahead and create it. Don't forget to dispose it when we're done. So now I'm going to go ahead and call display query, and this will be an untrained test, an untrained request. And we'll pass in our input vector, which is currently set to 0, 0, 0. So that should display the output from our network. And the way we do that is to call our neural net.query and pass in the input vector. We'll capture that result as an output. And now we're going to put in the right-len to display this on the screen. We'll start by displaying our experiment title. And then as a string, we output the input vector. So that's the vector that we queried against. And the output vector. Okay, so I'm going to go ahead and save off the neural net unit now. And we'll put a readlen in so that we can see the results. And I've got an error. I realize here that I need the reintroduce. And if we run our query, we'll actually get an error when we run it because we've not initialized any of the vectors yet. So that's our error coming back. So let's go ahead and correct that. And in order to correct that, we're just going to put some kind of a result coming back from our query. So I'm hard coding a return value here of 111, and you'll see that when we output the vectors as strings, they're actually quite long. They have several decimal places on the end of them, and I think my first attempt here was to do a vector to round, and this is just going to round out the values. This is a utility function in the vector library that's going to round them out to zeros and ones. Okay, so let's create some vectors for our network. The first thing we're going to need is the input layer vectors, the output layer vector, and the hidden layer vector. Okay, we're also going to need the matrices that tie these together. So we'll have hidden layer or hidden weights as the matrix between the input and hidden layer, and output weights as the matrix between the hidden layer and the output layer. Now I'm also adding here a hidden bias. You'll remember in the slides I talked about having a bias value and an output bias. So these vectors are biases for the entire layer. This allows us to have a different bias for each neuron in the hidden and output layers if we wish. We're only going to be using one value across each of the two layers. Now our inputs are a vector of size 3 because we have 3 binary inputs. Our hidden layer, as we discussed in the slides, is of size 4. So we're going to have 4 hidden layer neurons. And then our output is going to be another 3 element vector. Okay, so how do we scale the hidden weights matrix? Well, this matrix has the same number of rows as there are elements in the hidden layer, and the same number of columns as there are in the input layer. So when declaring a matrix, we put in the number of rows first and then the number of columns, not columns rows as you might expect. Our hidden bias is going to be the same size as our hidden layer of neurons and is going to have a value of 0.35, and our output bias is going to be the same size as the output layer, and it's also going to have a bias of 0.35 for each of the elements. Okay, so that's our basic types. We now need to randomize the weights in the hidden and the output matrices. And this is because if we started with them all as 0, then effectively our network could not learn, because 0 doesn't multiply by anything, and so it would basically hinder the learning of our network. So we're going to go ahead and randomize these by putting in a new method, which is randomize a matrix. This is going to be a straightforward loop through the rows and columns of the matrix just to set random values. Now remember that the ideal here is to set random values between 0 and 1. So what we're going to do is a random value within the range of 0 to 100, and then divide that by 100 to give us a decimal between 0 and 1. Okay, so we now essentially have everything we need in order to initialize our neural network. Let's go ahead and begin working on how to create the correct result from our query. So we're going to use the assign method here to assign the input variable to our inputs layer. So that's just going to go ahead and copy the values from the input parameter to our input layer. And then in the hidden layer, we're going to do the hidden weights dot product with the inputs. We then call the hidden layer to add our bias. So this is the point that we just do a simple addition of the bias values to the input to the hidden neurons, and then we're going to call hidden.sigmoid to activate that layer as a sigmoid activated layer of neurons. Now we move on to the output layer, and we're effectively doing the same thing. This time we're going to use the output weights. We're going to do a dot product with our hidden layer. We're then going to add our bias. And finally we'll call the sigmoid function to activate the outputs, and then we need to return that result back to the caller. So we're just going to copy those results back out with result.assign and f outputs. Okay, so now we should be able to run our query and see the results come back. Let's go ahead and take a look. And you can see that for the value of 000 we got 111, which is essentially completely random. I'm just checking here that what I got back was actually the product of computation, but effectively we're getting 111, which is completely incorrect, and we could have gotten just about any values, but when rounded we've got a 50-50 chance of getting a 0 or a 1, and in this case we're getting all 1s. So we are now ready to start training our network on our training data set. Okay, so now what we're going to do is we're going to query the network again. But this time when we query the network, we're going to get a measure of how accurate the network is compared against some desired output value. So what we're going to do is create a new input value, 000, and we're then going to create the output value, or the desired output value, of 001. So when I query the network with input 000 and I tell it that I want 001, the neural network is going to perform some calculation to give me a measure of how accurate the results are from the network. And the way I'm going to do this is actually to override the query method with another query method that returns an error measure. That's going to be a float, and it's worth pointing out that float is actually an alias of double in the vector library. Now, regardless of what type of floating point you pass into the library, you're always going to be passing in a double precision, regardless of the implementation. The implementation may only support singles. We're going to pass in doubles, and the library will do the translation for us. And what we get back from this is a total error value. Now, we didn't discuss this in the slides, but the total error value is just a measure of how accurate the network is, and it's based on the computation that we do for the delta for training our network. So I'm going to create this new override of query with an input vector and a desired vector, and as a result it's going to return a float, which is the measure of how accurate the network is. Okay, so effectively what this method will do first is to actually query the network the same as the previous version of query did. So that's going to return our output vector. Now, in order to calculate the measure of how accurate the network is, we are going to have to compute our delta. So we'll do f error delta, so I'm going to make this a vector on as a private member of the class, is equal to desired less output. So that's giving us our delta. Okay, so our total error can be computed using the squared error function, which is the error delta multiplied by the error delta and then multiplied by 0.5, so divided by 2. And then if we take the sum of that total error vector, that's going to give us our measure of how accurate the network is. Now, as you'll notice here, f error delta is a private member on the class, so we've already computed the delta that we're going to need to begin training later. But for right now, we're going to try and write out this total error value. Now, the problem with writing this value out is that it uses a lot of decimal places in precision, and so we're going to need a function that will convert it into a string, and float to str is not sufficient here. We're going to need to use the str function, the str string function. Initially, I tried rounding the error, but I clearly wasn't thinking straight. When I run this code, of course, it rounds out to either 0 or 1. So we get a total of error of 1. That's not useful for us. That's not precise enough to see what's going on. So what I'm going to do here is create a function which is safe round, for want of a better name. We take our value as a float and return a string. And we're just going to use the str function with an accuracy of 4 places before the decimal and 16 after, and that's going to be our result string. So then if I take safe round and put that into my writeline, now when we run this we get an accurate measure of 0.64971. So that's actually our error measure, and what we want to do is minimize that value. So we're going to try and reduce that down to some minimum value that says that our network is trained. Okay, so now it's on to the fun part where we train our network. Now the way that we're going to do this, we'll have a train method, and the train method will have an input value and a desired output. We're then going to display the result of training the network by calling display query with an input. And finally, we're going to write out the total error measure again. And that means that we need to get total error back from our network, so we're going to have to get that result from our train method. So let's go ahead and build the train method. So our train method is a function, train, input vector, desired output vector, and returns a float, which is the measure of how accurate the network is after training. Alright, so the first thing we need to do is query our network, and we need to do this to ensure that the delta error is calculated when we call query with an input and a desired output. So that's going to get us our delta, which is stored in f error delta, as you'll recall. So now, because we have our error delta, in order to get the gradient for manipulating our matrices, we need to calculate the derivative of the output layer. So I'm going to create a new vector here, derivative output vector, and we can calculate this as derivative output assign. So we're going to assign the outputs vector. It's just going to copy our outputs vector into derivative output, and then we access the derive sigmoid or sigmoid derivative method to derive that sigmoid function. And now we're going to calculate the gradient that we need to apply to our network adjustments. Now the gradient, as you'll remember, is simply the derivative output multiplied by the error delta for the output layer. So we'll have gradient output. We need that vector to be declared. And that value is simply the derivative output multiplied by error delta. Okay, so now we have pretty much everything we need to adjust our output weights. So we're just going to create an adjustment matrix. So this is going to store the adjustments that we're going to later make to our output matrix. And this matrix has to have the same dimensions as our output matrix. So the matrix connecting the hidden layer to the output layer. All right, now we need to layer our hidden layer neurons in rows across the adjustments matrix. You'll remember that we layer our neurons horizontally across the matrix here. And we're going to repeat this for each row in the matrix. I decided not to use a loop here just for clarity. I'm going to repeat each of these as a separate instruction. And then we need to multiply each of those values in columns by our gradient vector. So column 0 gets multiplied by the gradient vector, as does column 1, column 2, and so on. Okay, so we now actually have the adjustments matrix for our hidden to output layer. We need to multiply that by our learning rate, which we've not yet introduced into the network. So let's go ahead and introduce that learning rate value now. We'll create a class member for it. And then in the constructor, we'll go and set this to an initial value. Now, if you're wondering about the values that I've used for my biases and the learning rate here, these values are from experimentation. There's no sort of, or at least I'm not aware of any kind of intuition behind how to come up with these values. They're really just the product of experimenting and seeing what works. And so now we're going to start on our hidden weight adjustments. So again, we're going to need an adjustment matrix for the hidden weights. This time the matrix dimensions need to match the matrix between the input layer and the hidden layer, so our hidden weights. We'll go ahead and add this variable locally. And now we need to begin working back from the output layer. You'll remember we can't simply create a derivative for this layer. We also need to create a gradient based on the gradient calculated for the output layer. So what we're going to do is start by deriving the hidden layer neurons. So that's going to give us our derivative. That's the size of our step. And then we're going to calculate the gradient. Now, in order to calculate the gradient, we're going to need an additional matrix. So I'll go ahead and put this derivative vector in first, a new gradient vector for our gradient to be calculated, and then we're going to need to transpose the output layer. So we're going to have outputs transposed as a matrix. And to calculate the hidden gradient, we're going to start by setting our outputs transposed to the output weights dot transpose. So that's going to give us the transpose of the output weight matrix. Now our hidden gradient is the dot product of the outputs transposed. That's going to be the outputs transposed dot product with the gradient output. So the gradient we calculated before is computed with a dot product on the outputs transposed. That gives us our new hidden gradient. Now this hidden gradient then needs to be multiplied by our hidden layer derivative. So that's giving us our error signal multiplied by the step size. And then for the adjustments, we're basically going to repeat the same process as we did last time, but this time we have to remember that our matrix is a different dimension. So in the previous, the output adjustments, we were dealing with a matrix which was 3 rows by 4 columns. In this case, we're dealing with 4 rows by 3 columns because we're in the input to hidden layer neuron matrix. So we're going to go ahead and layer our input vector across that adjustment matrix and then multiply each column by the gradient that we just calculated. And here, of course, we need to multiply by the learning rate as well. And now that we have the adjustments for both the hidden and output layers, we just want to apply those adjustments. So we'll take the output weights and subtract our output adjustments. and we'll take the hidden weights and subtract our hidden layer adjustments. Now we're going to run our query one more time, and the reason we do this is it will recompute the total error for us, and we can return that as a result. So each time we train our network, we'll get a new total error value to tell us how accurate the network is after training on that one data point. Okay, so let's run our sample, and you can see there 0.631924. It's just slightly more accurate than it was on the previous run. So that's good news. Now what we need to do is repeat our training. Okay, so I'm creating a train epoch, and I've misspelt that. I'm sure I catch that later on. But we're going to create a training epoch which is going to train on every possible input for our neural network. And then we'll repeat this training epoch, train one epoch. We'll repeat it over and over again until our neural network reaches a satisfactory total error level. So we're going to try and reduce that total error level to some minimum. So we're going to start here with an input and desired output vector, and we'll internally just call train on that input and desired. And then I need to repeat this, so I'm going to sum the total error here because I'm going to repeat it 7 times. So I'm going to just put all of this on one line and repeat this line 7 times, one for each of the possible inputs. Okay, so our first input 0, 0, 0, our second 0, 0, 1, our third is going to be 0, 1, 0, and so on. And I'm just setting the inputs and outputs to match our training sample. Okay, and now as my result is the sum of those 7 iterations, we'll divide it by 7 to give us our total error after training one epoch. Alright, so back in our code here, we're going to start with training one epoch and see how that input comes out. And there I caught the little typo on the name. And this time 0.469, you can see that because we've given it several samples, we've got a much improved error result there. So all that's left is to repeat that until the error is below some predetermined minimum. And we'll set that at 0.05 for now. As we discover a little later, 0.05 is not small enough, but let's go ahead and train to 0.05, and then when I spot the error later, we'll reduce that value. For each iteration of training, we're going to output the total error, so we should be able to see the error decreasing as the loop progresses. And then finally, we're going to query the network for its results, but we're going to query it this time for every input that we care about. And we'll simply display each of these in a query using our display query method, and that's going to show us whether or not the network is accurately trained. Okay, so we run it and let's see what happens. We can see that the error is decreasing and we get our results. But if you look here at the fifth line, 100 generates 101. That's correct. If you look at the fourth line, 110 is creating 110. That's not correct. So what we need to do is go back and train a little further. Now I do here go in and check our training data just to make sure that we are training on the correct numbers, which we are. And so having determined that our training data is correct, I'm going to go ahead and just set the total error, the target total error, to a lower value. So we're going to go ahead and change this to 0.04, and when I run it again, we reach an accurate result for this line, and if we double check, all of these lines give us an accurate result. We've trained our network to count in binary. Okay, so let's take a look at what we saw here today. I introduced how artificial neural networks relate to real neural networks, how to feed forwards a neural network computation, so how to query a neural network, how to back propagate an error signal for training that neural network, and we've discussed the different types of neural networks and their possible applications, so regression problems, classifiers, and unsupervised or auto-encoding networks. If you'd like to learn more about artificial algorithms, or maybe about my dark vectors or DE compute frameworks, do keep a watch on digitalenvysoftware.com. I'm going to be fleshing out the development there over the coming weeks and months. Okay, so now I'd like to thank you for following along with my session, and I'm open to questions.